Hello, everyone. My name is Rangin Basu, and I'm a grad student at North Carolina State University. And I'll be talking about the FabScalar RISC-V version that we are going to release in a few days. So what is FabScalar? FabScalar is a tool that lets you generate synthesizable RTL, Verilog or system Verilog, for arbitrary superscalar core configurations within a canonical pipeline. So these are out-of-order cores, and the vision behind FabScalar was to accelerate the development of single-ISA heterogeneous multicores, which was a research topic our group was pursuing right around 2011. So it was released in 2011, and since then it has been widely adopted, and we'll talk about that in a few minutes. Besides being a tool that lets you generate out-of-order cores, it also is open source, and hence it makes superscalar technology accessible to everyone. Turns out out-of-order cores and superscalar cores are kind of hard to do. So this is a tool that will help you in getting started quickly. It's a research framework that lets computer architects estimate cycle time, power, and area with high fidelity. Since it's RTL, you can just run it through standard CAD flow and get these numbers easily. It can serve as a way to validate and to proof of concept your new microarchitectural techniques and its effect on the whole core. It can serve as a tool for process technology-driven research, for example, process variation, near threshold computing kind of stuff. And then you can always use it to prototype on an FPGA, or if you choose to do an ASIC, you can do that too. This is the outline of my talk. I'll talk about the tool set and the approach it takes at generating the out-of-order cores. Then I'll move on to talking a little bit about the other tools that come with it. I'll talk a little bit about the FabScalar outreach and who is using it, how many people have downloaded it so far. We and some other folks did some chips with FabScalar-based cores, and I'll show you some pictures and die photos of those. Then I'll move on to the evolution of FabScalar from the release version back in 2011 to the current version today in 2015. And then, of course, the reason I'm here, I'm going to talk a little bit about the RISC-V port of FabScalar, its microarchitecture, and a little bit about performance as well. So what is the FabScalar approach? How does it generate the out-of-order cores so easily? Turns out FabScalar, at least the released version of FabScalar, has a library of stages, and we call it the canonical pipeline stage library. Each stage has a few different designs in it with different microarchitecture for each stage. And the designs mainly vary in complexity, like superscalar width and the structure sizes for the different RAMs and CAMs. So some of the stages are also sub-pipelined to let you hit the frequency target that you need to get to. And then there's, of course, the stage-specific design choices, for example, speculation techniques, for example, an issue technique, and recovery mechanisms. These are just examples. There are other things that you can choose from. So the core generator tool then picks one design from each stage from the CPSL and stitches it according to the superscalar template, the canonical superscalar template, and gives you the core that you want. So the core type that you want is it's input by the user, and the core generator will just pick designs and stitch them. So this is an illustration of how the core generator works. On the left, you can see the CPSL. So I'm just showing fetch, rename, and issue. And each stage has a few different designs. Some are pipelined, some are not, 2 wide, 3 wide, et cetera. And then the idea is that you want to customize your core for the application you want to run. So You do some performance evaluation, decide on what core type you want, and then you input that into code generator, and it'll just pick and choose. It'll just stitch the different stages into a pipeline, and you have your synthesizable RTL of customized core. Another example of the same thing, but picking different designs this time for a different app. So what are the tools offered by the released version of FabScalar? Well, we have already talked about the CPSL and the code generator. Besides that, there's a memory estimation and layout generation tool, and we call it FabMem. Mind it, it's tied to the free PDK 45 nanometer, so it's not, I mean, you cannot use other processors with it. It's just for exploration purpose. It supports highly ported RAMs and CAMs, which are pretty pervasive in any out-of-order superscalar design. It has an estimation tool that does some sort of design space exploration before coming up with the optimum array layout. And it'll also generate actual physical layouts that are LVS and DRC clean for the free PDK 45 process. Then there's FabFPGA. It's a framework and a flow for prototyping FabScalar generated cores on FPGA platforms. So this is the user data, at least user data through October 2014. Since its release in 2011, more than 230 researchers from 22 different countries have downloaded FabScalar and have used it in some capacity. The figure B is the number of downloads. And there are three very distinct peaks, and those are basically coinciding with important events in FabScalar history. The first peak is when the ISCA paper was released in 2011. The second one during the micro topics publication, and the third one is when a class at Penn State used FabScalar for a class project. We have a Google group for discussion, and it's pretty active going by the statistics that you can see here. Interesting stuff. We took out-of-order core design very seriously, and we built 2 chips with the FabScalar generated core so far. The first one is called the H3 chip. OK, there's a caveat. So these are not RISC-V cores. These were built 2 years back, and these are still based on FabScalar PISA. So PISA was ISA from back in the 90s, and it's a RISC ISA and very similar to RISC-V. So the first chip is the H3 chip, which is a heterogeneity in 3D. That's what it stands for. The goal was to have 2 cores with different microarchitecture, out of order, of course, and stack them in 3D so that they're very close by physically, and you can have fast thread migration between them, constantly switching at very finer granularity. We are on our way to build a 3D chip, taping it out next month. But last year, we did build a 2D test chip of that same concept. And this is the picture of that particular chip. If you want to know more about the research, you can always read the ICCD paper that's referenced here. The next chip, which we got back this spring, is another one. It's a 4-wide superscalar, but it can be reconfigured dynamically at runtime to become a 2-wide or a 1-wide microarchitecture, turning things off and resizing the structures to be smaller or larger, depending upon what program you're running on it. So it's basically an adaptive microarchitecture, and it adapts to the workload to try and improve efficiency. These are the layout and the floor plan. And we had a warp talk at ISCA this year about this. This is a zoomed-in version of the floor plan. And this was fabricated with the 130 nanometer process from IBM. And it's a 5 millimeter by 5 millimeter die. We synthesize it for about 100 megahertz, since we are not really pushing for frequency. This is an example, or this is one of the non-NCSU-based chips. based on FabScalar. So in the last couple of years, we have also ported FabScalar to MIPS32 in our search for a more improved software toolchain. And there's also a version lying around somewhere that runs a subset of x86 as well. So May University did a MIPS32-based chip. It has coprocessor 0 and can run Linux. It has L1 caches that communicate with the AMBA-based system bus through AXI-like interfaces. Now I'm going to talk about how FabScalar evolved from the released version to the current version that we're going to release in a few days. So there are some obvious problems with the approach that we took back then. And the first problem was the CPSL approach. And in order to make a bug fix or a very small change, you would have to modify all the different designs for a stage and also modify the scripts in order to generate the correct design. Our solution for that was a monolithic system Verilog-based design that we call Superset core. It is still parameterized to do the exact same design types that the CPSL could do, but it's still one monolithic system Verilog thing. And you just need to change certain defines to get it to make it look like the core that you want to. FabScalar did not have multi-core or SoC support. By that I mean it did not have L2 caches, no coherence, or a system bus. Professor Sasaki from May University and his group, they contributed two very important tools, the Fab cache and the Fab bus. The Fab cache lets you generate arbitrary cache hierarchies. And the Fab bus lets you generate a system bus, which runs the AMBA protocol. And you can easily connect the FabScalar core, the cache hierarchy, and the Fab bus to give you a complete system. The next big problem, and this is a real problem, was that PISA ISA is very old, including the toolchain, which is stuck at GCC 2.7. And it cannot even compile the benchmarks that we want to run right now. Plus, it does not have a privileged ISA spec, so we couldn't even run Linux on it. That's why we decided to move to MIPS, and we ported FabScalar to MIPS32 2 years back, and we also added FloatingPoint to it. So there are two versions, MIPS32 and MIPS64, and one of them, the MIPS64 version, had the FloatingPoint support added to it. But then again, MIPS ISA is a proprietary ISA, and we were afraid that releasing it will result in a bunch of litigation, so we couldn't really open source that design, and we were looking for alternatives to it. Thankfully, by the great effort of the guys at Berkeley, RISC-V came along at the right time, and we jumped on the bandwagon, basically, and decided to port FabScalar to RISC-V. That will give us access to all the software stack that have been built around it. And it has a privileged ISA spec, so we could run Linux on it and take advantage of the great ecosystem, software ecosystem. This is what the FabScalar Superset core looks like. It can be maximally configured to be an 8-wide out-of-order superscalar core with various different structure sizes and pipelining as you choose. So there's a defined file that the user has to modify to tell the synthesis tool or the simulator tool that what the core design that the user wants. And accordingly, it will do a superscalar core of that dimension. So the example here is a 4-wide front end and the 3-issue back end. So you can do arbitrary combinations. You can do 2-issue front end, 2-wide front end, and a 4-issue back end, although that doesn't really make sense. So here's another example with different structure sizes. You can set the structure sizes to be any power of 2 number. Actually, for most structures, you can even do non-power of 2, but at least for now, we are restricting it to be a power of 2. So now the important part, this is the reason I'm here. So I'm talking about the RISC-V port of FabScalar. What are the changes we had to make in order to get FabScalar to run RISC-V instructions? The starting point was the FabSc Superset core, which had 64-bit instructions and 32-bit address and data. We decided to go with the RISC-V 64-bit, as that seemed to be pretty well supported by the tool chain. It has 32-bit instructions and 64-bit data, so there's a flip that happened. Well, not surprisingly, we had to change the iCache size, the fetch stage, and the BTB to match the switch of instruction size from 64 to 32, and the switching of address and data from 32 to 64. The register file increased, the physical register file increased in size, or actually doubled in size. The load queue, store queue, and the data cache also increased in sizes. And everything that comprises the data path, the execution path, had to be modified to handle 64-bit operands. After that, trying to fetch and decode RISC-V instructions meant we had to change the decode and the execute state. Fortunately, RISC-V is very similar to the FabSc ISA, so we did not have to make much changes in the rest of the pipeline, except for a few changes here and there to allow different formats of immediates to flow through properly. The fetch unit changed due to slightly different encoding of control transfer instructions and the way calls and returns are handled in RISC-V. We took a hierarchical decoding approach, wherein we are decoding just based on the major opcodes in the decode stage, and rest of the decoding is done at execute. The execute can be sub-pipelined, so you can also, it's probably not a huge hit in frequency. Previously for FabSc, all the decoding was done in the decode stage, and the instruction just flowed through the pipeline after that. This was pretty helpful, as it made the design kind of clean. Floating point. The FabScalar FabSc did not have a floating point unit, although the MIPS version did. So, of course, we want floating point, and since RISC-V had both 64-bit registers for floating point and integer register files, we decided to go with a unified physical register file approach. This simply means that everything is treated as the same type of instruction, basically, and the pipeline does not need to know about which, where the instruction has to go, except for the rename stage, which had to be modified to handle 32 additional logical registers. From the point of view of the issue queue, and there's also the additional committed state. Since we have 64 logical registers now, the additional committed state. For that, we need to add some space in the physical register file as well. From the point of view of issue queue, FloatingPoint LU is just another function unit. And we did not do our own hardware implementation of the floating point function units. We leveraged whatever we had from Synopsys, basically designware. And we are still testing it, and so far it has worked pretty well. The FabScalar test harness kind of looks similar to the Berkeley designs in that it's still a tethered design. The test bench communicates with the front-end server through the HTIF interface. We emulate the MMU and the system control registers, or the CSRs, in C++ code, but we do have plans to add RTL implementations of these when we do the privileged spec implementation on FabScalar. So far, we have only run micro benchmarks, and efforts are underway to run spec on spec and more complex benchmarks on the FabScalar RISC-V course. I'm just going to show a small micro benchmark which we handcrafted to basically pump the pipeline with as much independent instructions as we could just to make sure there are no obvious performance bottlenecks in the pipeline. So this is a simple array reduction, and we hand-coded the assembly, so it kind of looks silly. But the instructions are perfectly aligned at 4 instruction boundaries, so that you can pump 4 instructions every cycle through the 4-byte superscalar configuration. And with that, we get an IPC of 3.7, so there doesn't seem to be any obvious performance bottleneck in our core. So the most important thing, what does FabScalar have to offer to the RISC-V community? Well, it's an open source tool to generate out-of-order processors. It's highly parameterized and implements the RV64G instruction set. It comes with uncore components, the fab bus and the fab cache that you can use to build a full system on a chip. And we will also release the verification infrastructure along with whatever limited amount of test cases we have. And one important thing that needs to be done, we need to add more test cases, as Christopher correctly pointed out. We'll also release the CAD flow to streamline synthesis and place and route if anyone is doing that kind of thing. There's a C++ timing simulator, which is cycle accurate with the FabScalar code. And it's also highly configurable. You can just change a defined file, and it'll simulate like the core you want it to look like. Everything will be available on GitHub this coming fall. So feel free to download them, use them, hack on them, and commit back. So if you want to build a healthy community around FabScalar and RISC-V. So in future works, we want to implement the privileged ISA to boot Linux successfully on the FabScalar cores. And of course, similar to what the low-risk guys are doing, we want to untether the FabScalar core so that it can be an independent SoC. We need to add more test cases to stress design features. And I cannot stress enough on this fact because we face serious problems when we are trying to do the chips. Test cases are very important, and some kind of infrastructure to run them efficiently and in an automated way. Also, efforts are underway to port FabFPGA, which is the framework to emulate RISC-V core or FabScalar cores on FPGA. FabFPGA to RISC-V so that it's easy to emulate your design. So you can just generate a core using FabScalar and then push it through the flow, and it'll just run on FPGA. Here are the references. If anyone is interested, there are a bunch of papers related to FabScalar. I would encourage you to go read about them. And I'll open up the house for questions.
So for the open source release, do you know yet what license you're looking to use, e.g. Apache, GPL, etc.?
Well, we haven't decided that yet, but it'll probably be the same license that the Berkeley designs are released with. So you are free to use it in a commercial design if you want to. Yeah.
Rishir Nikhil from BlueSpec. I have 2 questions. One is when you say timing analysis, this is for when running some code, how many cycles it would take, that kind of analysis, or is it a technology analysis for the particular ASIC flow?
Yeah, technology analysis.
So, how many megahertz I can run it at, that kind of thing? Or?
Sure. I mean, which one are you referring to? Are you referring to the C++ simulator? Or?
Yes, you said C++.
Oh, no. That's a timing simulator. By that I mean it's a cycle accurate C++ simulator, basically. We call it, it's called a timing simulator.
Okay, so this is for figuring out IPC studies and things like that.
Yeah, for performance studies only.
Okay, and then with respect to the technology time, clock speeds, etc., what's your experience so far in what you've done?
I'm sorry, can you
how fast have you been able to synthesize these things? Do you anticipate any issues there?
So a dual issue out-of-order core, I was able to synthesize with 45 nanometer commercial technology at around 1.8 gigahertz. And a 4-issue synthesizes at slightly lower than that. If I remember correctly, 1.6 gigahertz, I'm sorry.
Do you have hardware that runs that fast?
No, we don't. So we haven't taped out with the 45 nanometer.
I want to go to what you just said about the 1.8 versus 1.6. So 1.8 is a 2-wide core, and 1.6 gigahertz is a
It's a
4
4-wide, yeah.
and this is issue width, right? This is the issue with the maximum number of
So yeah, so both front end and back end with the 4.
So can you speak a little bit more to how you handled, the parameterizability in the FabScalar core, on whether these are two separately designed instances and whether the tick defines just choose one versus the other, or is it more parameterized than that?
Yeah, so the one that you'll currently find on the web, the release version, which was released in 2011, it literally had different designs that it chose from and stitched together a pipeline. But right now we have like you can think of it as an 8-wide superscalar out of order core, and you use parameters to remove stuff from it. So it literally is an 8 wide out of order core. Thank you.